Okay, we are live. Hi, everyone. My name is Yoland. I work on Google Play Search on the machine learning projects, mostly focusing on retrieval and ranking models. And today, the topic is on deep retrieval for Google Play Search. This is a zero to hero edition, which means hopefully, even if you have no context or very little knowledge in the machine learning domain, by the end of the talk, you should gain decent amount of understanding on how ML models works in general and how they're applied in the space of search and recommendation. So the goal of today's talk, there will be four major areas. First is we're going to go through sort of a typical recommender systems from the non-deep linear models to the DNN-based models. And afterwards, we're going to move to DNN search retrieval. And the third part would be a comparison between the DNN deep learning-based retrieval versus the traditional retrieval. In the end, we're going to look at some fun visualizations and extensions of these deep learning models. First, I want to go through some of the terminologies we'll be using today, just for better context. The first thing is query. Query means input stream, and it's commonly associated features for a given query. Example over there would be, let's say the query is Facebook Messenger, and their associated features will include things like unigram, bigram. Unigrams for Facebook Messenger would be Facebook, the token Facebook, and the token Messenger. For the tower, in our context, means a feed-forward neural network, either for query, user, or app. And embedding its general common understanding of its meaning, embedding is mapping from discrete set to a vector space. For example, for the embedding Facebook Messenger, it might be a mapping towards a series of numbers that represent this specific query. So to go into the first part, before we dive into the deep learning-based retrieval, I want to take a step back and first take a look at some of the traditional recommender systems. So one type of recommender system is content-based filtering. Let's say we have a problem of recommending a set of apps to users. The content-based filtering basically means you can take these sets of apps and break them down into specific attributes and features. For example, the apps set we have over here, Tinder, can be broken down into the feature having the characteristic of dating, casual, made by Match.Inc. And similarly for all the other apps. So from this perspective, you can see essentially an app embedding in a very binary sense is basically a series of numbers that represents that's either 1 or 0 to represent whether an app has a certain feature or not. So in this case, the app embedding for Tinder will be 101 010. Based on this kind of a feature breakdown, given an existing user, we can take all of their install history and the app's feature in their existing phone and try to match towards other similar characteristics within your inventory, within the general set of apps you have. For example, this given user here named Michael Scott is interested in dating and casual and match app. Therefore, Tinder is in the end the you can basically calculate the dot product between the two embeddings and get the final recommendation score for this user for this app. So in this case, will be 3. So there are clear limitations for this approach of content-based filtering. First, you have to handcraft these these features. You have to have specific domain knowledge. So the quality of the recommendation truly depends on the quality of your domain knowledge and feature engineering. And it's also very limited to existing interest for the users. For example, if Michael Scott has never installed productivity-related apps, our system will never recommend productivity-related apps for him. So another way to do this is called collaborative filtering. Instead of breaking down the set of inventory, set of things you're trying to recommend to users by its characteristics, what you can do is utilize your existing users to find similarities within there. This approach is very popularized by the mid-2000 Netflix Prize, which is a competition to compete for the best collaborative filtering algorithm to recommend movies to users. So in this approach, what you can do is take a set of existing users and their preferences and their interest and utilize that to calculate the probability of a new user installing or being interested in certain apps. For example, in this context, we can break down the apps and the users into sort of adultness or gameness. And by breaking down these things, in the end, the probability of, let's say, this given user, how likely it will be interested in installing a certain app will simply be the dot product of these two embeddings. So as you can see over here, the app embedding will be simply the adultness and gameness of this app. And how you calculate these embeddings and scores, there's a specific technique called matrix factorization, but this is beyond the scope of this talk. If you're interested, there will be probably will be a link in the description of this video, and you can look more into it. And in real production, you wouldn't have these adultness or gameness as a feature, but over here it's just for easy representation of the app embedding. So once you have these type of embedding, a really interesting and cool way to do things is that you can potentially plot it. In this graph, if we take the adultness and gameness of an app and users, we can group them into the same dimensionality. And as you can see over here, Michael Scott is quite close to the Monopoly app. So probably a good recommendation for him. So this approach also has its limitations. One being that you're not taking advantage of a greater set of user features. You are directly creating this mapping from the user ID to its embedding, and similarly for apps. How do we take advantage of some of these user queries, user features? Well, this is where the deep learning softmax model comes in. Within the deep learning softmax model, what we can do is take the user's features and its embedding and create a user tower, feed-forward neural network. And in the end, at the final layer, after the last layer of this model, what we can do is multiply it with the matrix of a set of weights for each single app and run it into the softmax function to sort of create a representable score. But essentially, what in this case, what it's doing is taking the um, individual output of the last layer to cross with every single weights in this matrix. So this matrix itself is basically a mapping of all the app IDs to its embeddings. So what about if people ask, what if I want to use more features on the app side? This is only utilizing, one matrix table that's representing the mapping from apps to embedding. What about, all the apps related features? This is where you can create a two-tower architecture by completely replicating the user tower into a app tower and creating another set of feed-forward neural networks to propagate these features in the end to a final layer. And on top of the final layer, you can take the two towers result and either do dot product or cosine similarity to calculate a score. And that score, it will be your prediction of likelihood of user installing certain apps. So the benefit of this comparing to the previous sets of approaches, you're fully utilizing user features, app features. You can, you don't really need to handcraft certain characteristics or having domain knowledge. You do need to do some amount of feature engineering to get good results from this model. And in the end, you just need to take your existing set of users' install history to train this model and group the user and app into the same dimensionality. So at this point, you might be wondering, today's talk is about deep retrieval for play search. Why is recommender system related to the search at all? I would say, great question, Dwight. The reason is because if you look at the architecture of this model, the two-tower model, what you can see is that what it's trying to do is grouping the user and apps into the same dimensionality by running through a feed-forward neural network. What you can potentially do is completely swap out the user tower to a query tower. And in that case, what you're essentially doing is taking a set of queries and query strings and what users are searching for and grouping that together into the same dimensionality with the apps. So the excuse me. So the result of this is that in the end, what you can potentially get is something that can nicely group all of the related queries and apps together into individual different clusters. As you can see over here, the query fun games is grouped with a set of gaming apps and also RPG, and relationship is grouped with Tinder and wedding planning app and enterprise apps over here. So the reason this is incredibly beneficial and utilizing this architecture will help quite a bit is because that there are 3 steps you can create this architecture and very efficiently use it. First is you train this model to group them into the same dimensionality. Second is you, during an offline process, not doing the serving stage, you can map all of the apps to its embedding because you have all of the apps and its features already. So you generate this app ID to embedding table. In the end, at the serving time, what you can do is only calculate the vector for query and utilize that to find the nearest neighbor. And how do you do that? you basically can, utilize certain type of fast vector search algorithm to given a query embedding, find the nearest neighbors. So essentially, this entire process of training model is almost like a compression of compressing query strings and apps and all its features into a set of numbers. And at the serving time, you don't need the app tower at all. You only need to calculate the query embedding, and utilizing certain type of fast vector search, you can take advantage of this architecture and gain significant speed and memory improvement in your search stack. This is a very fun animation of how it works in a books context. So you train the neural network and you can map all of the books into its embedding space. As you can see, King Lear and Romeo and Juliet is right over here. And at serving time, you calculate the query embedding and do the vector search and to find its nearby neighbors. So one thing worth mentioning is a very key component in this equation is the efficient fast vector search. The great part of that is recently Google has released its very state-of-the-art efficient vector similarity search algorithm called SCAN. It was only released, I think, half a year ago or a year ago, and it's really powerful. As you can see, this is its performance in a approximate nearest neighbor competition, and at the bottom, the axis is basically the recall score, and the y-axis is the speed. As you can see, at a very high recall, it's still able to achieve significant amount of speed, or given a speed requirement, it achieves a really high recall score. So this is something that if you're interested in taking advantage of this type of architecture and the fast nearest neighbor search, definitely check out SCAN. So by now, I hope you have a good understanding why we went through the entire journey of traditional recommender system and its DNN approach, and how the two-tower architecture it eventually was able to influence the deep search within the Google ecosystem. But before you jump into this hype train of utilizing deep learning into retrieval and search, I do want to help you to take a look the pros and cons in this equation when comparing machine learning based retrieval versus the traditional retrieval. So the traditional keyword frequency search, or the inverted index search, is basically taking a bunch of documents. Let's say these documents over here we have are sentences. And we take the frequencies of each individual tokens and map them to the docs they appeared in. For example, beats, I take the frequency of 1 and appeared in the document 1. Dwight is 2 and appeared in document 1 and 2, blah, blah, blah. Now, given a specific query, Dwight beat, we can go through this table of mapping and take all of these tokens and reversely find either a union or an intersection of the docs that has all of the tokens we have in the query. So in this case, we can easily find doc 1. As you can imagine, as this scales up into hundreds and thousands and millions of documents, inventories, set of things you want to search and find, it costs a lot of memory to store them, to scale this up. And this is frankly why a lot of open sourced solution around how to scale up the inverted index search exists. Because they are able to figure out ways to cluster them or architect these algorithms in a way that's efficient and fast and costs less memory. However, with the deep learning approach, as you remember from earlier, what we are able to accomplish is that we can compress all of these, both the queries and the apps, into a series of numbers. And in the end, utilizing the fast nearest neighbor search to achieve decent result. What this can get you is that you no longer need a lot of memories to store all these tokens and features. All you need to store is a set of numbers. And there are clear pros and cons in both type of approach. For deep learning based retrieval, obviously it's very fast, and the serendipity the benefit of this approach is that sometimes, because you're compressing things into a set of numbers, it's very easy for it's very sometimes it's very interesting. It will generate very interesting results. That's probably a better way to put it, because everything is within this dimensionality. Things are grouped up in a very sensible way from time to time. One example we had previously in this type of approach is that during our training, we realized the model was able to learn this. In English, LOL means laugh out loud. In Korean, actually, people also do this kind of shortcut to represent characters. So a lot of Korean web users or mobile users will only type half of the characters to represent the full character. And in our deep learning based approach, we're able to learn that this kind of, without any human input, we're able to learn that the half characters are representing the full set of apps. However, as a lot of you might know, the machine learning, deep learning based approach comes with its cost. So a lot of times there's also the opposite of serendipity result, which I looked up. In this case, it's called Zemblanity. And because of this training process, takes iteration and iteration of data. You don't know where things went wrong, and sometimes the result you retrieve are not as solid, as good. And obviously, this approach is very data dependent. Without data, you wouldn't be able to train and group things together. So the traditional keyword frequency retrieval, it requires no data. It's not a black box. Anything that went wrong, you can always debug and figure out which token, which specific indexing caused this retrieval, caused this problem. Why isn't certain document retrieved? So these are very easy for you to debug, but it has the downside of memory and scalability. So that concludes the third part of machine learning based retrieval versus traditional retrieval. The last part, we're going to look at some of the fun visualizations and extensions of our model. One thing is that if we run this through the CPA, what we can do is realize to sort of reduce the high dimensionality of these models into very small component into the 3D world. And as you can see over here, it's actually pretty interesting that in the end, after we finish training the model, all of the social media apps are grouped, clustered very nicely over here. And I think some of them are games over here, and some of others are the email and productivity related apps. So another interesting thing we did within Google internally is we created this effort called Spirit Name. What it does is that it can utilize your name and run it through the deep learning retrieval model to find the top result that is in the embedding space closest to your username. So in the end, we were able to get a lot of interesting mappings from Googlers and its name to their spirited app. And we create these badges within our system to represent their spirit app. So one last note before I finish today's talk is the reason why I wanted to present the deep learning, the machine learning based retrieval and recommendation is because I think a wise man once said, there's an overfitting in machine learning world on image problem. I think this tends to be true even earlier, but now it's less and less so. A lot of people are very passionate going to the academic career to research and learn more and develop more techniques on the image problem because these are the fancy, cool things you can show your friends. But there's huge amount of market or capital involved in the recommendation and search system. So if today's talk interests you, there are a huge amount of top products with demands for recommendation and search and machine learning in this area. And if you're passionate about that, definitely look more and learn more from it. Here are some of the resources that is mentioned today. I would highly recommend the Google Machine Learning Recommender course, which is largely what a lot of today's content is coming from. And also, as I mentioned, the very impressive efficient vector search retrieval algorithm called SCAN. And here it's links and some of the papers I recommend. And this is all of the Spirit app for all of the people who worked on this project. Thank you all. And if you're interested in reaching out to me, talk to me, here are my handles on Twitter and GitHub. Feel free to ask me any questions over there. Thank you very much.